So now we're going to talk about how we compute the discrete time Fourier transform for discrete time periodic signals. Now, if you recall, the way we started out in the beginning of the chapter was that we define the Fourier transform for aperiodic signals. However, just like our treatment in the continuous time case as well, it turns out that the Fourier transform is much more, can be generalized, and it can be applied to both periodic signals as well, aperiodic signals in general, as well as to periodic signals as well, by using some special representation, some delta functions in the frequency domain. And therefore that would allow us to describe both periodic as well as aperiodic signals using the same common framework, which is the discrete time Fourier transform. Now, in order to move further, let's just consider the most the basic of discrete time periodic signals, which is a complex exponential. Let's say if I had e raised to power j omega naught n, which is a periodic signal, so omega naught divided by 2 pi is rational. It's clear that this signal is neither finite energy nor is it absolutely summable, and therefore we can actually conclude that the Fourier transform for this signal will not converge. And despite this, we're going to use delta functions to provide that common framework, just as we did in the continuous time case. Now, if I were to try to compute the Fourier transform for this using the synthesis equation or the forward Fourier transform, I run into a bit of a problem in the sense that if I compute this x of e raised to power j omega, this is summation n equals minus infinity to plus infinity, and this is e raised to power j omega naught n times e raised to power minus j omega n. So this is just simply e raised to power minus j omega minus omega naught n, and I basically run into a problem in the sense what does this summation evaluate to? I mean, this is an infinite sum. Does it converge or does it not converge? And you can clearly see that at least when omega equals omega naught, this sum should not converge. It actually diverges all the way up to infinity. But what happens when omega is not equal to omega naught? Or what does it equate to? Now, this is difficult to figure out just by looking at this summation, even though I would encourage you to try to think about it. It can be done in this forward manner. But the way we're going to do it next is to venture a guess in the Fourier domain using a delta function, and then try to verify that delta function residing in omega naught, if I take the inverse Fourier transform, that will indeed be e raised by j omega naught n, which is exactly what we did in the continuous time case as well. So that venture guess is the following. Let's consider x of e raised to power j omega as an impulse in the Fourier domain, which is 2 pi delta omega minus omega naught, as we did in the continuous time case. That's an impulse residing at the frequency omega naught radians per second. However, a little bit more of a thought reveals that this actually is not a valid discrete time Fourier transform. And the reason why it's not valid is because the discrete time Fourier transform needs to be periodic with the frequency, with a period of 2 pi in the frequency domain. And this signal, as you see here in the Fourier domain, is not periodic. So in order to make this periodic, that venture guess has to be modified a little bit. And that just includes periodic copies of that impulse. So this is omega naught minus k times 2 pi. So in other words, if I were to sketch this Fourier transform out in the frequency domain, so let's say this is the x-axis, which is the frequency. There's an impulse residing at omega naught, and then there's another impulse residing at omega naught plus 2 pi, and so on and so forth. There's another impulse residing at omega naught plus 4 pi, and the heights of each one of these impulses is 2 pi, and so on. So similarly, on the negative side, this is omega naught minus 2 pi, and so on and so forth, and so on and so forth, right? So that at some point here, all the way up here, could be, this is omega naught plus some integer multiple of 2 pi, and so on and so forth. So this would be just a generalization of that. So this is the Fourier transform, which is our test signal. Let's just try to find the Fourier transform for the inverse Fourier transform for this. So yeah. So in order to find the inverse Fourier transform with this, I just use the analysis equation. So this is 1 upon 2 pi, and then this is an integral over a length of 2 pi. And then this is x of e raised to power j omega times e raised to power j omega n, and then integral with respect to omega. If I plug the test transform here, so this is summation k going from minus infinity to plus infinity. This is delta omega minus omega naught minus k times 2 pi times e raised to power j omega n times d omega. So in other words, in order to find the inverse Fourier transform, all we need to do is we need to evaluate this integral. And this is pretty straightforward to evaluate, and the reason is because this integral is over any interval of length 2 pi. And this could be anywhere, regardless of what the starting point is. It could be from 0 to 2 pi, it could be 2 pi to 4 pi, it could be from any omega naught to omega. So it could be any delta to delta plus 2 pi, as long as that interval is around 2 pi. So let's say I were to, and one of the other key observation is that within that interval of n 2 pi, there will only be a single impulse function residing in that interval, because the impulse functions are always uh, located 2 pi apart in the frequency domain. So within an interval of 2 pi, therefore, I would only have a single impulse function residing in that integration limit. So let's say this interval of 2 pi that I had was somewhere over here. So this was here and here. This is where I was integrating, and this was length 2 pi. And with this interval, of course, I just have a single delta function, and therefore the shifting property is going to kick in. And what I'm going to get, so there's a 2 pi here, sorry, it's 2 pi here. So this 2 pi is going to cancel with this 2 pi. The shifting property is going to kick in, and this will just simply be equal to this thing here evaluated at omega equals omega naught plus 2 pi m, because the integration is over the frequency variable. So this turns out to be e raised to power j, and instead of omega I have omega naught plus 2 by some integer m times n, and so this is e raised to power j omega naught n times e raised to power j 2 pi times some integer, and that's clear that that must be equal to 1. So what we've been able to verify that x of n is indeed equal to e raised to power j omega naught. And so our conclusion is what? The conclusion is that if I give you time domain signal, which is periodic and is e raised to power j omega naught, and if for discrete time Fourier transform for that is equal to 2 pi times this summation k is minus infinity to plus infinity delta omega minus omega naught minus k times 2 pi. And this is enough, this result is enough for us to be able to compute the Fourier transform of any periodic signal. And the reason is because any periodic signal that I give you in this case, in the discrete domain, will have a Fourier series representation. So this is x of n is, so any periodic signal can be written as x of n as being equal to summation k over any interval of length integer n, capital N, which is that is a period, a sub k e raised to power j k 2 pi by capital N. And so in other words, any discrete time Fourier, in any discrete time periodic signal can be represented as a superposition of these complex exponentials. And for each one of those complex exponentials, I know the Fourier transform, and then I can just apply linearity to it in order for me to be able to determine the Fourier transform of any periodic signal. Instead of me generalizing this further, what I'm going to do next is just give you some examples to illustrate this point.